So it's my great pleasure to talk here and try to share with you some interesting stories. So I hope I can pronounce these two great people's name as well as Anton, but unfortunately I cannot. So I'm gonna call them KZ equations. So this is an equation studied, introduced in the study of 2D CFT, and it has been intensively studied by many people in the past 30 years. In particular, its monodromy representations is related to quantum groups following Kono and Drimfield. Of course, also among other peoples, also related to the representation of affine Lie algebras following Kazhdan-Lustig, also related to hypergeometric or multi-dimensional hypergeometric functions following the work of Tarasov and Vachenkos, and so on. And there are, generalizations of KZ equations, like the cycloatomic KZ equations. The KZ equation is associated with a Lie algebra, and the cycloatomic KZ equation is associated with a symmetric pair. And just as KZ equation is related to quantum groups or bright groups, the cycloatomic ones are related to quantum symmetric pairs, as well as bright groups in some other types. And there is another notion of quantum KZ equations introduced by Igor Frankl and Rasha Tihin in the study of quantum affine Lie algebras. It's sort of a finalization of KZ equations. So all of these things and its relations between the monodromy of these equations with Yang-Baxter and the reflection equations have been understood and has been studied by many people in the past decades. But somehow, all these equations have some irregular singularities. So it means that given any solution of these equations, the solution gonna have different asymptotics in a different sector region near the irregular singularity. And the difference of the asymptotics is measured by some matrix called the Stokes matrix. And it seems the study of Stokes phenomenon or the Stokes matrices of these three types equations are missing in the literature. So in this talk, I basically give I basically talk about the Stokes phenomenon of these equations. So this is not hard work, but probably it's a new viewpoint. And since this is a workshop on higher structures, so in the end, I will try to mention some words on higher structures like this BV quantization or L infinity algebras, although I may not be an expert on it. So the outline of my talk is, I'm not assuming everyone is familiar with Stokes phenomenon. So first I'm gonna give an introduction to ODE with irregular singularities. And then in the second part, I'm gonna study the Stokes phenomenon of these three types equations. And in the end, as I said, I'm gonna mention some words on higher structures. So first, let's see what's the Stokes phenomenon. So there is some general method in the study of ODEs to solve. It's a so-called resummation method. So it's a procedure to get a finite result from a divergent sum. So probably the most well-known resummation method is a so-called Borel resummation. So suppose we are given a formal Paul series f hat, which is given by fk times zk, and you take a summation. And let's assume that the norm of the coefficient is bounded by k factorial. Then we can formally rewrite this formal sum. In the second step, in the second equality, we replace this k factorial by the gamma function. Then we formally, switch taking sum and the integration. So in the end, we get the integral expression. So this is called a resummation, Borel resummation. So if you look at this expression, let's denote this expression as Borel sum along some direction d. So this d is simply a direction from 0 to infinity. So if you look at the integrand, so since fk is the norm of fk is bounded by k factorial, therefore this function as a function of tz is actually holomorphic in the unit disk. Therefore, as long as we can take the analytic continuation of this function, defined in unit disk to infinity along this direction d, so we have a chance to make sense of the integral. So this is a so-called Borel resummation. And let's see an example. So suppose we have this Euler series. So this is basically given by k factorial times z power of k. And then this integrand, if we look at this expression, we will find out this integrand is actually 1 over 1 minus t. And now we can choose the direction d as a negative real axis. Then in the end, this integral expression gonna give us a holomorphic function in some sector region, in some proper region. So this is one example of Borel resummation.
Xiaomeng, sorry, I have a naive question about this this last integral. So you have exponential of minus t, and if you integrate it over the negative,
probably I want to say,
yes,
probably it's exponential t. Yeah, you should choose the direction.
Something, yes, something should.
Of course, yeah.
Okay, thank you.
Yeah. Right. So this is a very general method to solve ODE in the Power series method. So now let's go to a more complicated example. So let's consider the following linear system of ODEs. So this is ODE defined on the complex plane. So where f is a matrix value function, and u, let's assume u is a diagonal matrix, and v is an arbitrary matrix. So this is simply an n by n system. So note that it has an irregular singularity or second order pole around origin. And we're gonna study its behavior, the behavior of the solutions near z equals to 0. So a simple fact is that this system has a unique formal fundamental solutions, which takes the following form. So let me explain what's this singular part. So this bracket V simply takes the diagonal part of matrix V. And H hat Z is a formal power series of matrices starting from identity matrix. So each of these H1 and H2 and so on are some constant matrices. So if we plug in this expression into our system, we're gonna solve all this coefficient matrix in a unique way. But somehow the problem is that if we look at the norm of these matrices, we'll find out the norm of HK is more or less k factorial, which means that it's H hat Z is in general divergent power series. It's only a formal sum. Yeah. But as we have seen, so given this formal sum with this sort of good bound on its coefficient, we can use the Borel resummation to try to get holomorphic solutions in some proper regions. So basically here we use the Borel summation we just introduced. Then the formal sum will be replaced by the following integral. So this integral is the integration from 0 to infinity along some direction d. And if you work a little bit, you will find out the right-hand side always gives a holomorphic function for all the direction d in some proper region, for all the direction d, but finite many ones, which are given by the argument of the difference of all the ui's. Recall that this ui's are simply the diagonal, are simply the eigenvalues of the matrix U. So basically, the Borel sum of H hat gives a holomorphic function for all the directions, but finite many ones, which are called the singular or Stokes directions. So in another word, if we take the sectors bounded by two adjacent singular directions, then in each of these sector, we're gonna have, in each of this sector, this borrow sum is a holomorphic function. Therefore, if we take the multiplication of this borrow sum with a singular part, we're gonna get solutions to our original system. And these solutions are unique in the sense that they are asymptotically equal to the unique formal sum at the singularity. So this basically says that if your equation has an irregular singularity, then the solutions exist but are not unique around the singularity. So from an equivalent viewpoint, you can say that any solution of the system gonna have different asymptotics in different sector regions. It's equivalent to this fact. And now we want to measure this sort of jump phenomenon of the canonical solutions. And to do that, we're gonna take the ratios of the canonical solutions in different sectors, and their ratios will define some constant matrices, which are called Stokes matrices. So basically, we take any two opposite sectors. Recall that these are sectors bounded by singular directions. We take any two of them and the corresponding canonical solutions on it. Then we can simply, for example, we can simply take the solution F plus in R plus, and then we take the analytic continuation of F plus to another sector R minus in a positive sense. Then we compare these two solutions in R minus. So this is basically what this first identity means. Then we know that S plus as a ratio of common solutions to ODE must be a constant matrix. Similarly, we can define S minus. So these two matrices are called the so-called Stokes matrices, which measure this jump phenomenon. And yeah, so let's see an example. Let's simply take the 2x2 case, where this matrix U, as I said, the leading term is a diagonal matrix. Let's say it has entry U1, U2, and V is a 2x2 arbitrary matrix. Then one can verify that the Stokes matrix S plus is given by this matrix, where this lambda1, lambda2, these two complex numbers are simply the eigenvalues of the residue matrix T1, T2, B1, B2. So if you look at this expression, you will find out the Stokes matrices as a function of U and V, right? As a function of the residue and the leading term, highly transcendental functions. Actually, this is more or less the only case people can write down the Stokes matrices explicitly. In the rank 3 case, even in the rank 3 case, people cannot write down the explicit formula. Yeah, so this is sort of the difficulty in the study of Stokes matrices or Stokes phenomenon. Yeah, so everything is highly transcendental, but somehow all these transcendental functions has some algebraic properties, which is quite interesting. Yeah, I may give a comment later on, like they may be described by some algebraic integral systems and so on. So this is a quick introduction to the so-called Stokes phenomenon of a meromorphic ODE. Yeah. If there is no questions, I gonna move to the second part of the talk.
Oh, I forgot. I'm sorry. Is it easy for you to drag your file in the chat so people can look back on your formulas? Is it easy? If it's easy.
Yeah, I think so. I will.
Thank you.
Right. Yeah. Okay. I think. Yeah, it works.
Great. Thanks.
Have you got it?
Yes, we got it. Thank you.
Great. Somehow I forgot how to back to the full screen. Okay, great. Yeah. So, yeah. so this type of equations is all we need in this talk. So this linear system with a second order pole at the origin. Yeah. Now let's move to the second part. So I'm gonna study the Stokes phenomenon of certain KZ equations and explore its relation with Yang-Baxter equation and reflection equations. So let's first give a summary of what's inside my second part. So basically, I'm gonna study 3 types of meromorphic ODEs, which are called KZ or cycloatomic KZ and quantum KZ equations, respectively. And then I'm gonna show that the Stokes matrices of these guys satisfy Yang-Baxter and the reflection equations with and without spectral parameters. So this is the final result. Now let's give more details. So first, let me introduce what people called KZ equations. So the KZ equation is associated with a Lie algebra, let's say GON in my talk, and with the Casimir element omega. So this omega is basically the dual of the pairing on GON given by the trace. Yeah. In other words, you can take the elementary matrix EIJ, and then omega is simply EIJ times EJI. You take a sum for all the IJs. And then we take the diagonal matrix U and the arbitrary representation of GON, V. And associated to this data, we can define the KZ equation for a function with n complex variables with valued in V, the representation of GON in V tensor n times. So this is the equation for this function, which takes the following form. So here is this upper index I means that this U acts on the ith component of V times n. So through the representation of GON. And omega ij simply means that omega, which has 2 components, acts on the ith and the jth component of V times n. So this is how we define these equations. And one can verify that this is actually a compatible system of equations. And also note that this is a linear system defined over the space of distinct points. All right. So it has some singularities when Zi equals to Zj. And therefore, if you take any solution of this equation and take the monodromy, take the analytic continuation of this solution along any loop on the space of distinct points, we're gonna get fundamental group representations. And also, as you may know, the fundamental group of this space of distinct points is simply the Bride group, which has a generator B1 to Bn-1 with the following relations. So each of this, for example, Bi is simply a path taking the transposition of Zi and Zi plus 1 coordinates. And right, and now our goal is to study the monodromy representation of these equations. So which is simply a Bride group representations on the vector space V tensor power of n. So to study the monodromy, first we have to choose a base point. So we're gonna take a base point at infinity, which means that all the complex variables Z1 to Zn are around infinity. And just as one variable case, just as in the ODE case, so this system have a formal solution around infinity, and whose borrow resummation will give us different solutions in different asymptotic regions, which means that there exists canonical solution F sigma. I don't know if you can see in the left bottom corner F sigma. And this sigma is an element inside the permutation group. So there exists a unique solution F sigma, holomorphic solution F sigma, which is asymptotically equal to F hat inside the following asymptotic zones. So this is similar to the one parameter case. And now to get the monodromy representation or to get the bright group representation, we simply take the ratios among these solutions labeled by the elements inside the permutation groups. So for example, to compute the monodromy along BI, we should take the ratio between F1 and the F sigma I plus 1. So this F1 is a solution assigned to the asymptotic zone where Z1 is much less than Z2 and much less than Z3 and so on. And F sigma I and sigma I prime is a solution assigned to the same zone, except that we require Zi plus 1 is much bigger than Zi instead of much less than Zi. And to compute this monodromy, we can simply fix, because this monodromy is sort of local, we only care about the behavior between Zi and Zi plus 1, we can fix the other coordinates. Then using some simple trick, the factorization property, this problem is reduced to the study of the monodromy of the following equations, right? Because if we fix the other points, we only have 2 points left. If we denote by Z as the difference of these 2 points, our KZ equation, this equation is reduced to an ODE, which takes this form. And now for this ODE, we need to find its solutions with prescribed asymptotic around infinity. So recall that this is simply so for this ODE, F is valued inside V tensor V. So this is simply a linear system of ODEs whose Stokes matrices was explained in the first part of my talk. And recall that for this ODE, for this system of ODEs, it has 2 solutions with a given asymptotics, right? And then its monodromy, or the ratio between these 2 solutions, is given by the Stokes matrix, which we denote by S plus. Now, since the function F is valued inside V tensor V, the Stokes matrix is valued inside endomorphism V tensor twice. So eventually, the monodromy along the path BI of the KZ equation is simply given by S plus X on the i's and the I plus 1's component of V tensor N, right? Because BI is an endomorphism on N on V power of N. And we need this S plus to X on its, which has only 2 components, to X on its i's and I plus 1's component. And now since all the generators BI satisfy the Bride relation, in particular, B1 times B2 times B1, right? In this Bride relations, this B1 times B2 times B1 must equal to B2 times B1 and B2. So as a simple consequence, we find out that for any fixed U, which has different eigenvalues, the Stokes matrix of this equation gonna satisfy the Yang-Baxter equation. So this Yang-Baxter equation is another way to state the Bride relation for the BIs. Yeah. So this is basically this is basically a way to compute the monodromy representation of KZ equations, the linear systems we have seen in the last page using the Stokes phenomenon. So let's see an example. So let's take the Lie algebra to be GO2 with the natural representation, with the vector representation. Then our KZ equation, then this ODE can be written as a 4x4 linear system. Because this function is valued inside V tensor V, which is 4-dimensional now. So given a basis in V tensor V, we can write U as a diagonal matrix whose first 2 and last 2 entries are same. And then the residue matrix takes the following form. And the Stokes matrix of this guy can be computed explicitly. And then we will find out the Stokes matrix takes this form. So one can also verify it directly by hand. It's S plus satisfy Yang-Baxter equation. So this is one simple example. Yeah. So this is the relation between the Stokes phenomenon of KZ equation and the Yang-Baxter equation. So as I said, there are many different types of KZ equations. So for example, there is another type of KZ equation associated with a symmetric pair instead of Lie algebra.
Xiaomeng, just if you return to the previous slide, maybe just naive questions. So you say that S plus has this relatively simple form, and then before you were showing us this 2x2 example with a rather complicated off-diagonal element, right? With scary gamma functions and so on.
Yeah.
How is it? What happens to all of this here?
So if you look at this thing, so this 4x4 system is reduced to a 2x2 system.
Yes.
And two trivial ones. And this 2x2 system, well, you use the fact that gamma z times gamma 1 minus z is given by sinh function, something like given by sine function.
So it's a particular, so then even the 2x2 one simplifies.
Yeah, exactly. So recall that these two guys, using the Euler, maybe Euler's formula, these two gamma functions, when one is z, one is 1 minus z, it's given by sinh function, sine function. Yeah.
Okay, thank you.
So this is sort of algebraic thing you can see from, Actually, it's a very interesting question to compute the Stokes matrices via some integral formulas. Yeah, and there is a way to compute them actually. Yeah. Okay, so now let's go to the other cases. So as I said, there is a KZ equation associated to a symmetric pair SON and GON. So let's think of SON is a fixing locus of some involution on GON. Then we take the omega k, which is the invariant part and the involution of the omega, the Casimir element. Or simply you can write down the explicit formula. It's simply given by this guy. And then we take its image inside U SON by multiply these two guys. So this is the Casimir of K. So given these two least theoretic data, as well as the representation of GON and the SON, one can introduce the following so-called cycloatomic KZ equation. Now for a function with n variables valued inside the W tensor V power of n. And it takes the following form. So again, we use a notation that U power of I means that U acts on the ith component of V. So here we index the W component by 0. So this is W is a 0 component. Therefore, this omega k 0I acts on, it has two components. The first component acts on W, and the second component acts on the ith component of V. So one can verify this is a compatible system of equations. But it's a slightly different with KZ equation because it's defined on the points on the space of distinct points over the punctured complex plane. Therefore, if you study its monodromy, it will give a representation of the bright group on the punctured complex plane, right? So which is a fundamental group of the complement of the singularities of this equation. And for this bright group on the punctured complex plane, it has the following generators, where all these BIs are the same as before, simply switching the Zi and Zi plus 1 coordinates. But this tau is a new guy, which is a loop surrounding the origin or surrounding the origin. And this bright group has, with these generators, will satisfy the following relations. So the second and the third one is simply the bright relations. And the new guys are the first and the last one. And we can basically use the same method to like the Stokes, using the Stokes matrices to study its monodromy representation. And note that each of these equation has irregular singularity around the infinity. So here in the introduction part, I put the irregular singularity around at z equals 0. But in all these equations for convenience, I put the irregular singularity around the infinity. So this is a small change of notations. And the monodromy along each of these BI is same as before, because to compute the monodromy along each of these BIs, we can forget the second term. We can forget this term and the last term. So it is reduced to KZ case. So the new thing is how to compute the monodromy around the tau. So recall that the tau is a path of Z1 surrounding 0. And it reduces when we compute this monodromy in a local picture, we can forget all the other points. Then the cycloatomic KZ equation gonna reduce to this guy, right? If we forget Z2, Z3, and so on. So the equation which are left is simply this part with Z1. Therefore, we get this equation. And this is another ODE with an irregular singularity around the infinity, which has a Stokes matrix. And this Stokes matrix corresponds to the monodromy along the path tau. And now using the relation inside this group, for example, using the first relation, we know that tau B1 equals B1 tau. And recall that this monodromy of tau is given by the Stokes matrix of that equation, while the monodromy along B1 is given by the first Stokes matrix of the KZ equation. Therefore, one simply sees that for any U, diagonal matrix U with distinct eigenvalues, the Stokes matrix of this ODE gonna satisfy the reflection equation. So this reflection equation was introduced by Knizhnik in the study of certain quantum system on half-line. So this is a Stokes phenomenon. This is a result on the Stokes phenomenon of cycloatomic KZ equation. Okay, and now the monodromy of cycloatomic KZ equation was studied by many people like Ulrichs and another speaker of this workshop, Bushier. And I found out in his abstract that he may also talk about the Drinfeld-Konel theorem, something related to this theorem. So I leave the Drinfeld-Konel part of the monodromy of KZ equation to his talk. And so this is the Stokes phenomenon of the second type KZ equation. Now let's turn to the quantum KZ equations. So the third type of KZ equations. So to introduce this KZ, to introduce this equation, let's take a representation of GON, and let's take a meromorphic function on a Riemann sphere, which is given by 1 plus omega over Z. Recall that omega is element inside GON times GON, and via this representation, we can think of it's a real element inside this linear transformation. And then the quantum or QKZ equation is actually a difference equation instead of differential equation. Now for n variables functions valued inside of V times n. So which takes the following form. So it's sort of lengthy formula, but as I said, this is a difference equation. So if we take the step for the parameter Zm, so we're gonna get a difference equation whose coefficient is given by the multiplications of this element R, where again this Rm m minus 1 means the two components of R acts on the m and m minus 1's component of V times n. And one can verify this is a compatible system of difference equation. And inside this equation, this parameter P, this step P, and the kappa are certain fixed parameters. And again, this U is we take this U as a diagonal matrix. And this U power of m means this term acts on the m's component. And as in the general principle, if we have a difference equation, and we can take its limit to get a differential equation. This is true for this QKZ equation. So actually, if we let p goes to 0, we're gonna get a KZ equation. So to be more precise, if we set this parameter kappa to be exponential of some parameter h times eta, then we let we introduce new parameter y1 to be h times z1 and yn to be h times zn. And then we take these new functions. Then the resulting QKZ equation is in terms of this new function can be written as follows. So here basically we plug in this expression, then one can see that now our difference equation for these new variables takes the following form. And therefore it's easy to see that when h goes to 0, right, we move this 1 to the left, then we divide both hand side by h, then we use the definition of differential, we will see that this QKZ equation in the limit will become KZ equation. And now our goal is to study the monodromy of this difference equation. So it's sort of tricky question because.
And this short question, are these QKZ also have some geometric background? Are there connections over there so that this monodromy makes sense, geometric sense?
Yeah, if you look at the coefficients, its coefficient in this case its coefficients is rational, right? So the singularities is also along the diagonals. If you look at.
I'll see you later.
Yeah. Right. As Chen Chang asked, so it's tricky to talk about the monodromy of difference equation because given any solution of this equation, if you multiply on the right, if you multiply the solution on the right by any p periodic functions, you're gonna get another solution. Therefore, in general, the ratio between two solutions is not a constant matrix. It's not a constant guy. It's a periodic function. Yeah, which gonna depend on the parameters. And now this difference equation also has a irregular singularity. It's not so easy to see, but first we're gonna to compute the monodromy. We'll first reduce this to the ODE. So as before, so we can use the factorization property to reduce this QKZ equation to an ODE, to an ordinary difference equation, which takes the following form. So this is the coefficient is a rational function. So you can think of the irregular singularity is again around z equals to infinity. And for this guy, to start, this guy has a more or less has the same sort of Stokes phenomenon as the differential equation, analog. And actually, first one can find the formal solution of this difference equation, which takes the following form. And then Borkhoff tells us that this formal solution can resum to holomorphic solutions in different sector regions. In other words, there are canonical solutions, like actually meromorphic solution F plus, F minus, which are asymptotically equal to the given formal solution in the left or right half planes. So actually this proposition was known like 3 years earlier to the similar result on differential equations. And then given these two canonical solutions, Borkhoff considered a so-called connection matrix as a ratio of these two guys. And he also proved that now the connection matrix as a periodic function must be a rational function of exponential z. So which means that this connection matrix has a following form where S0 to S1 doesn't depend on z. So one should really think of this as the analog of Stokes matrices we considered. for the in the differential equation case. And then our theorem simply says that the connection matrix of Volkov satisfies the Yang-Baxter equation, but now with a spectral parameter, right? Because before the Stokes matrix is constant, but now we consider the difference equation. So their connection matrix depends on Z. Therefore, when we talk about its monodromy relation, everything will be with Z. So this is not surprising. So one can verify it satisfies sort of equations with parameters. And actually, as we said, in certain limits, the difference KZ equation will become the differential KZ equation. And along the way, this connection matrix will become the Stokes matrices for the KZ equations. So to be more precise, as we have seen in the limit, the QKZ equation we have seen here, this is in the second line, this difference equation will become this differential equation. And in the meanwhile, the element S0 and S infinity in the connection matrix SZ will become the Stokes matrices for this equation. So this was known probably to the Volkov. And one should really think of this S0, S infinity as a value of connection matrix SZ at 0 and infinity. And as a simple consequence, because S satisfies this equation, if you put Z1, Z2 to be 0 or to be infinity, then automatically you get solution of Yang-Baxter equation without a spectral parameter. Therefore, as a sequence, it implies that the Stokes matrix for the differential KZ equation satisfies Yang-Baxter equation without spectral parameter. Yeah. So this is basically.
I have a short question. So how is it? Does it mean that those spectral parameter dependent solutions of the Yang-Baxter equation that you're getting from this machinery, they will always be trigonometric solutions, right? Because they must be periodic.
Yeah,
is it right?
Probably by some cohomology argument, it's equivalent to the trigonometric, universal trigonometric R matrix for the affine quantum groups.
But then one can probably imagine a limit where trigonometric solution goes to a rational solution. Then what would it mean for the difference equation? Is there some way then to get also rational solutions, or not at all?
Yeah, that I don't know, because even in this case, this S plus, S minus are probably not rational solution. Yeah,
Okay.
I don't know.
Thank you.
Yeah. Okay, in the last 1 or 2 minutes, yeah, this is a review. I promise to say a bit of words on hair structures for this workshop. So on the one side, so there is some theory called 2D cohomology field theory, introduced maybe by Manin and Conservage, and it's sort of 2D TFT parameterized by the cohomology of the Riemann stable curves. And in a recent work, so this for mathematicians introduced a quantum 2D cohomology field theory inside the BV formalism. But the relation between 2D cohomology field theory with BV formalism was known before, much earlier, probably due to Conservage and Manin. And they consider a deformation inside this framework. Basically, they think of this 2D cohomology field theory as a solution of master equation. Then they consider quantum master equation. So a possible relation with this work is that, so following the work of Dubrovin, we know that under the semi-simple assumption, 2D cohomology field theory is one-to-one corresponds to meromorphic ODEs with its monodromy deformation. And actually, the second type of KZ equation, the cycloatomic KZ equation considered in this talk, is actually a quantization or deformation of this Dubrovin type ODEs. So actually, it gives a deformation of Dubrovin's ODEs, as well as the deformation of the 2D cohomology field theory, or equivalently the geometric picture, the Frobenius manifold. And somehow, as I said in a recent paper, these mathematicians introduced another way to do the quantization. So the possible it raises the following the question that if there is any relation between KZ type equation with this quantum, 2D TFTs. So this is one thing. And another thing, probably I'm short of time, so I will not say it, but it's basically a generalization of the Stokes phenomenon of KZ equation to the categorified KZ equation. It's some work in progress with Sheng and Chen Chang. Yeah, I guess my time is up. I stop here. Thanks for your attention.
Well, thanks a lot. So any reasonably short questions? So can you say at least one word about this last slide, because then we'll know what to ask you at the question session in the end.
Okay, so first there is first if we consider two-term L infinity algebra, which is a two-term chain complex, where G0 has a sort of Lie bracket, but the Jacobi identity is only satisfied up to some homotopy. Then Bai, Sheng, and Chen Chang introduce a solution, introduce a classical Yang-Baxter equation for this Lie2 algebras. One solution is a pair of data where R is an element inside G0 tensor G0, like in the classical case. And another element is inside these three tensors, satisfy some algebraic relations. So this is what they call a solution of probably Yang-Baxter equation for Lie2 algebras. And on the other side, as we know, the solution of classical Yang-Baxter equation gives rise to KZ equation. And these solutions of Yang-Baxter equation for Lie2 algebras actually gives rise to some flat two connections in the following way. So this is maybe following Martin's and his students' work. So given any representation of this Lie2 algebra, now which is a complex instead of vector space, so one can define the following two connections, where this Cn is a base, and this V power of n is a fiber, where A and B are, A is a one form, B are two forms over this space. And now A is the curvature of A is not zero, but up to some homotopy controlled by B. And the A is simply the KZ part, right? If you still recall what are the KZ equations. So basically this is the KZ equations. But B is now given by this another piece of data P is three tensor. It has three lower indices, and the omega ij are these one forms in the. So it's not hard to introduce this flat two connection. And now the question is, like the KZ case, to compute the monodromy representation of these guys. One new thing is that we should integrate this two form, this connection over some two-dimensional sphere instead of loop. But one problem is that the space of distinct points is cyclic. Therefore, if we consider two bright surface, like the two-dimensional bright in four-dimensional space, inside this space, the two-dimensional bright or the bright surface will have some singularities. This is some people call the movies or yeah. So it's sort of bright surface in some three-dimensional space. Therefore, it has some singularities. So the question is how to integrate these forms over these singularities. And in this categorified case, the monodromy relations will have will include the Yang-Baxter equations as in the classical case, but with many other, maybe 9 or 10 more relations. So this is something people call monoidal braided two categories, maybe, which has a defining relations like 9 or 10 defining relations, and all these defining relations should be realized as monodrome, as integrations over some circles with singularities. And we hope that Stokes phenomenon is a nice way to somehow resemble the singularities in some way. So eventually we would like to compute the monodromy, yeah, in some way. The difficulty is to study the singularities. Yeah.
Okay, thank you. I don't know whether there are any brief questions. Yeah.
May I?
Sure.
Hi, Dima Reutenberg here. Yeah, I was wondering, like, I think you just said that at the very end. Does this have any relation with the Zamolodchikov tetrahedron equations? We call this talk about two vector spaces, two connections, and braided monoidal two categories. Like, made me think of work of Kapranov and Voevodsky from way back when, like in the early 90s, I think. They were looking at this situation. So is this anything similar to what you're talking about just now?
Yeah, the name you mentioned reminds me, I mean, it's certainly a similar name, but I cannot tell you immediately what's the exact relation. Because there are a bunch of relations. I think there are three groups of people who defined this so-called braided monoidal two categories, as far as I recall. Probably Chen Chang can if I'm wrong, Chen Chang can. So there are three groups of people. They may use different, axioms, but each of them is consisting of 9 or 10 relations, which certainly includes this tetrahedron relation, but I don't recall it immediately. Yeah, I guess here what we followed is some reference in Martin's paper with his student Zero. Yeah.
Right. And let me mention that there was also some work by this Japanese, I forgot.
Kono.
Kono, yeah, exactly.
Yeah.
Isn't that he gave a talk last year in Giovanni's birthday on conference, isn't it?
So could I just make a quick remark?
Please.
Just very quick. So first of all, I'm Faria Martins. First of all, Lucio Siri was not my student, your colleagues in Lisbon.
Oh, sorry. Yeah, I thought.
As is fact. The second bit about the Zamolodchikov tetrahedron equations, you don't immediately get the solution of the Zamolodchikov tetrahedron equation because the framework here is not two categorical. The framework is bicategorical. So you do get a type of solution of the Zamolodchikov tetrahedron equation, but you must also insert some associativity morphisms. That's actually what the flatness of the two connection gives to you. Just two very quick remarks just to finish it up. So yes, there is the beautiful work of Toshik Kono on the application of the KZ2 connection to define invariance of braided cobordisms. In fact, I think he solved the singularity issues that you were mentioning at the end of the slide. And there's also another paper of someone called Arnaud Moutier, which is called the Kontsevich integral of order 1, in which he used some type of KZ2 connection to compute invariance of a particular type of knotted surfaces which are obtained by from knot isotopies. And he did also solve the singularity problem in a slightly different way. Yeah, sorry to intrude. That's all I needed to say. Thanks for the talk, by the way.
Okay, thank you. Thanks for the comments. So apparently I'm not an expert on these higher structure things. Yeah.